In this lesson, we're going to review the basics of functions. We're going to start off by looking at vocabulary, and we'll start with these terms. Independent variable is our input, while the dependent variable is our output. Our input is typically our x value, and therefore our output is our y value. And when we're looking at all the possible input values, that's our domain. And when we look at all the possible output values, that's our range. Oftentimes in calculus, we'll have questions that ask you to write a sentence. So here's one of those. If we said that the cost C of producing X air conditioners is given by C equals F of X, explain the meaning of F of 30 equals 1950. And so if we were writing our answer to this, we would write something like this. The cost of producing 30 air conditioners is $1,950. I do want you to notice I have a single sentence. It's complete and everything I need. And in particular, I have all my appropriate units used. Now, when we're working with functions, there are 4 ways to represent them. We can represent them with a table, graph, formula, and words. And not only do you need to be comfortable with all 4, you actually need to be able to translate between those. In this lesson, we're going to be looking at one example of each and the types of questions you might be asked. So our first example is a table, and this is the population of Minnesota every 20 years from 1860 through 2000. And our first question here is this a linear function? So we think back to our knowledge from Algebra 1, and we recall that if it had to be linear, it has to have a constant rate of change. We noticed right in here that we went up about 600,000 people in these 20 years, and in the next 20 years, we went up nearly 1,000. So clearly it's not linear because it does not have a constant rate of change. It does not have a constant rate of change. Our next question asks us, what are the units for the rate of change? Well, we should remember that rate of change is just another word for slope. Slope is delta y over delta x, which means our units are going to be our y units over our x units. So for y right here, we have thousands of people. So that'll be our unit on the top. And for our x, which is up here, we have years. So it's thousands of people per year is the units for our rate of change. Next question asks, which 10-year period was the rate of change the greatest? You'll recall we mentioned that right here it looks like we went up nearly 1,000 people in those 20 years. And as I look across here, I never go up anywhere near 1,000. The only one that's close is here, and it's around 850 or so. So we know that it was between 1880 and 1900 was the greatest rate of change. And if we wanted to actually calculate that, we would subtract our y's, so 1751 minus 780 over 1900 minus 1880. And we would then get, let's see, 971 over 20. All right, our last question on this says if this function was named p of t, so we're going to give it another name, p of t right here, which means we're going to call this t. So we've changed our independent variable to be t and our dependent to have the function notation p of t. What value of t would satisfy the equation p of t equals 4 million? Now, this was up in thousands. So if we think of this in terms of thousands, this is 4,000 thousands. And so we look up here, and where would we see 4,000? We're like, oh yeah, it would have occurred right before 1980. So our best approximation would probably be something like 1979. All right, let's move from table and on to graph. So here's a nice looking graph, and the first question we might ask about this is what is the domain and range of this function? So this one doesn't appear to go on forever, and we look at the domain, we can see our x values start here at 1 and end here at 11. So we might say that our domain goes from 1 to 11. I'm using square brackets here because it clearly is has a point at the endpoints. I don't have any asymptotes or anything on this one. Now for my range, I'm going to have to estimate here. This nearly goes to 2, and this goes a little bit below -2. So I'm going to guess that it's something like -2.2 to about, it looks like 1.9. Now in this case, I don't have exact values, so I use my best judgment on that. All right, let's take a look at the next question. Evaluate h of 9. You'll notice up here there was a name for this function, h of x, and 9 is going to be my input. So I go along my x-axis, there's my input, and then I go right here and I can see that h of 9, if I input 9, my answer is -2. My next question asks, for what values of x does h of x equal 0? This is like saying y equals 0. So I'm going to look for every place where y equals 0, and it appears to equal 0 here, and here, and here, and here, and again here. So we're going to put all those answers and we're going to estimate the ones we don't know exactly. So it looks like something like 1, 1.5, I'm thinking about 4.6, 7.9, and then 11. And we list all of those answers. All right, let's move on to an example with a formula. So here's a formula, f of x equals 1 over x over minus 3. And our first question is, what is the domain of this function? And what we need to remember for this is, of course, we can't divide by 0. So we know that this denominator, x minus 3, cannot equal 0. And if I solve this, that means x cannot equal 3. So my domain, and there's a few ways to write this. So my domain, we might say reals except 3. So that's one way to write it using words. Another way to write it would be, well, it's everything from -infinity to 3. And again, everything from 3 to infinity. So, and here we do not use the square brackets because it does not include the number 3. All right, our next question simply asks us to calculate f of 5, and all we have to do is plug it in the formula. So f of 5 equals 1 over 5 minus 3, and our answer is 1/2. Our last question asks, when does f of x equal 10? So we put 10 in for f of x. 10 equals 1 over x minus 3. Do a little algebra. I'm going to multiply both sides by x minus 3, so I've got 10 times x minus 3 equals 1. 10x minus 30 equals 1. I've got 10x equal to 31, and here's my answer. X equals 31/10. And that's a perfectly good answer. If you like 3.1, that'd be fine as well. All right, so our last example for a function is one that's described using words. So in this case, we've got a situation about braking distance. Braking distance for a car to come to a complete stop is directly proportional to the square of its speed. A car traveling at 60 miles per hour needs 180 feet to stop. All right, so let's talk about a reasonable domain for this function. This is about an actual car. We know that cars at their slowest could go 0 miles an hour, so that would be our minimum. And while I suppose we could go up to infinity, I think there's a limit to how fast a car could go. Maybe we put 200. I mean, that seems unreasonable, but there's our reasonable domain. Okay, so let's represent the situation with a formula d of v, where d is distance and v is the speed. Now, if you remember about direct proportion, that means that d equals k. We've got some constant of proportionality times v squared. So that's what this piece meant. Braking distance, that was d, is directly proportional, means we've got some constant here, to the square of the speed, and our speed was v, so times v squared. Now we got some numbers here, so we can figure out that k. So we know that 180 equals k times 60 squared, and therefore k equals 180 over 3600. Let's see, that probably cleans up nicely. Let's see, 18 is divisible by 6, so k would be, oops, k would be 3, and 360 divided by 6 is 60. Oh, that goes even lower. So let's see, I believe that's 1/20th. Does that make sense? Yeah. So our function would be d equals 1/20th oops, 1/20th times v squared. Okay, so let's go down below, and we're asked, well, what's the meaning of d of 40? Well, that would be the distance needed to stop if you're going 40 miles per hour. And then if we want to evaluate it, we can just use the formula. So that's going to be 1/20th of 40 squared. And let's see, 40 squared is 1600, and 1600 divided by 20 is 80. So we would be looking at needing 80 feet in this case. All right, hopefully that gives you some aid on remembering how to work with functions.